After discussing morphisms between ring spaces in general, now we want to apply this to the ring spaces we care about at the moment, namely open subsets of affine varieties. So we have the following proposition. If U is an open subset of the affine variety X and Y inside AN is another affine variety, then the morphisms from U to Y are exactly the maps from U to Y whose n coordinates are given by regular functions phi I on U. In particular, when we take the target Y to be A1, then, well, any map is allowed, of course, and then the only restrictions is somehow any phi I here works. And so this set here is just given by the regular functions on U, as we would hope. And the proof, we do it in several steps. First of all, we show that every morphism is of this form above, so its coordinates are given by regular functions. So let's assume we have a morphism F, and then to get these regular functions, we can actually extract them from F by taking the n coordinate functions from Y to K, which send this vector here to the ith component. These are clearly polynomials, so they are given by they give regular functions on Y. And then the phi I, the ith component, you can just get by pulling back this yi by the morphism F. In other words, the phi I is the ith coordinate of the map F. And then because this was a regular function, by definition, the pullback is also a regular function on the pre-image of Y, but the pre-image of Y is everything. So it's just U. And so phi I is indeed a regular function, and F has the desired form. That was one direction. We just plugged in the coordinates. And then now comes the reverse direction, that if you write down a map F of that form, then it is given, then it gives a morphism. And so we assume we have such a map here and all the components are regular functions. Then we check the properties of a morphism. Firstly, we check it is continuous. So for this, let Z in Y be a closed subset. So it's written as the vanishing locus of some regular functions gi on Y. Then the pre-image is given by the points in U such that, well, they land in Z, and landing in Z just means that all these functions here must vanish. So in other words, gi of our image point is 0, so we can plug in these coordinates. Now, here comes a subtle thing. So the gi are polynomials in the coordinates on Y. And all of these functions here are an O of U. And I claim that if you take a bunch of regular functions in O of U and plug them into a polynomial, you still get something in O of U. And the reason is that O of U is a K algebra. And plugging this into a polynomial just means you start multiplying them with each other, and then maybe also multiplying them with the coefficients of the polynomial, and then maybe adding a bunch of these things up. But all of these operations preserve regular functions, both multiplication with elements of K, and addition. And so this here is still a regular function. And that's a bit abstract. So maybe as an example, G might be such a polynomial here in the yi. The phi might be some regular functions, in this case actually given by actual quotients of polynomials. And then if you plug this in, well, you just enter these terms here, and then you see what you get is still a regular function because you can expand it and still gets polynomial divided by polynomial. So indeed, this here, this expression here is a regular function on U, and therefore, just rewriting this here is then the vanishing locus of the first thing intersected and so on until vanishing locus of the rth thing. These are regular on U, and then we had a lemma. In the script is lemma 3.4, which says that the vanishing locus of a regular function is closed in the open set U. And so this is closed, and then you have an intersection of closed sets, and so this is still closed inside U. So preimage of closed is closed, so F is continuous. The second property you want to check is that F pulls back regular functions to regular functions. So for this, assume that psi is such a regular function on an open subset W of Y. And then we want to check its pullback here is a regular function. And so we describe it around any point in the preimage F inverse of W. So let's say A is such a point with image point Y, which sits in W. Then, well, we use around the image the function psi is given by G divided by H for G and H regular functions on Y. And then the pullback, what does the pullback do? Well, we plug in the function F into the components of G and H. So F is given by the psi I, so we plug in psi 1 up to psi n into these terms here. And then by assumption, all the psi I are regular functions. So around now the point x equal a, they are given as quotients of polynomials in the coordinates now on x. And so what we have here is we have a polynomial plug in a bunch of quotients of polynomials, and then divide by another polynomial plug in a bunch of quotients of polynomials. And then you can imagine what you can do is you can expand all the denominators, bring everything onto one denominator. And then, well, you get exactly a quotient of polynomials in the coordinates x. And so this means that indeed, around the point that we considered, this is a quotient of polynomials in the coordinates on x. And so f star of psi is a regular function. And so f indeed is a morphism. And to give a concrete example here, you could consider x to be the vanishing locus of xy minus 1 inside A2, this usual hyperbola, and y to be A1. And then we can write down easily a morphism from x to y, which is send this pair to the first coordinate. That's a polynomial in the coordinates, so that's a regular function. That's fine. This is a morphism. And geometrically, this corresponds to, well, just remember an x coordinate, so it corresponds to projecting down. And then inside y, you have the complement of 0. And on that complement u, you can write down a map in the opposite direction, g. And so now this lands in A2. So you need to specify its 2 coordinates. And you take the coordinates given by x and 1 over x. So x is sent to x, comma 1 over x. These are both regular functions on u. And you can check easily that this lands in here, because if you multiply them, you get 1. So this equation here is satisfied. And so this is indeed function. It's given by regular functions in all of its coordinates, and it lands in the target x, so it gives a morphism. And the cool thing about these two morphisms here is if you compute the two compositions, if you first do f and then do g, so you first forget y, but then you know y is immediately determined as 1 over x, so you recover it, and so you get the identity on x, and similar the other direction. And so actually, these two affine varieties are isomorphic given by these two isomorphisms f and g. And here we see one reason why it was important to allow regular functions with denominators, because if we hadn't allowed 1 over x to be a regular function, then we couldn't have written down the inverse of this very nice map f, and that would have been a shame.